Welcome to the lesson on optimization. As usual, let's warm up first. So if you feel quite confident with what you've been doing the last two lessons, you might want to pause and try these out yourself and then just check them as you go. But I'll quickly talk you through them too. Use the rules of differentiation to find f dash of x, the gradient function, for f of x, the original function. So if f at the original is 5x cubed, the gradient function, multiply the exponent by the coefficient to make 15x, and then you subtract 1 from the exponent. 15x squared is a gradient function. Here's the original function, so separately differentiate each term. An x term just becomes a coefficient, 5, and 2 multiplied by negative 1, because that is negative 1 there, 2 multiplied by negative 1 is negative 2, subtract 1 from the exponent just makes x to the power of 1, and we don't bother to write the 1. X cubed, 3 times 1 is 3, and subtract 1 from the exponent, you get 3x squared. Don't forget to write the x. X terms just become the coefficient, 4. Half x to the 4, 4 times a half, you can put in the calculator if you want, you get 2, and subtract 1, you get cubed, so 2x cubed is the gradient function. X squared, 2 times 1 is 2, and that becomes x to the power of 1 when you subtract 1 from the exponent, so 2x, and then that's a constant term, so it just becomes 0, so we don't bother to write plus 0. X plus 1 over x, you need to flatten the function first, like last lesson. X is already flattened, that's fine, but this is x to the 1. Remember, you can make it positive by bringing it up to the top and making it 1x to the negative 1. So x plus x to the negative 1, and that's the original function still. Now do the calculus. That's 1x, so it becomes a coefficient 1. Negative 1 times 1 makes negative 1. X, subtract 1 from the exponent, you get negative 2. Here we need to break up the numerator first, so it's still the original function, make it x over x plus 1 over x. Then we need to cancel down if we can. X divided by x just becomes 1, and flatten the function. That's x to the positive 1, so bring it up to the numerator and make it x to the negative 1. Then do the calculus on the original function. Here's the calculus function, f dash x. That's a constant term, so it just becomes 0, so we don't bother to write it, it disappears. Negative 1 times 1 makes negative 1x, and subtract 1 from the exponent makes the exponent negative 2. Another one, say, these are just reminding you flatten the function first. X squared over x, break up the numerator first, x squared over x plus 5 over x, then do any cancelling down. X squared divided by x becomes just x. Flatten this part because you've got x in the denominator. That's x to the 1, bring it up by making it 5x to the negative 1. Then now do the gradient function. That's 1x, so it just becomes 1. Negative 1 times 5 is negative 5. X, subtract 1 from the exponent. That's the gradient function. Let's keep battling through these. 10 over x squared, you've just got to flatten it first. So that's x squared, bring it up into the numerator by making it a negative exponent. So that's 10x to the negative 2. And now the gradient function is going to be negative 20x to the power of negative 3. 6 square root of x, you can rewrite that as 6x to the power of a half, because you won't really be asked this in studies, but it's just interesting anyway. Square root is like the same as saying to the power of a half. So 6x to the power of a half, that's already flattened. Now let's do the calculus step. F dash of x is half times 6 is 3. X half minus 1 is negative a half. So you could have also had 3x to the power of negative 0.5, that's also okay. If you've got it in double brackets like this, before you do the calculus step, you have to have expanded and done the foiling. So that's x squared, this becomes minus 2x, that becomes plus 1x, and that becomes minus 2. And that, when you combine those like terms, you'll get x squared minus 1x minus 2. Now do the calculus step, f dash of x, 2x, that becomes 2x to the power of 1, minus 1. And then that's a constant term, so it just floats away. We've got to flatten this one first, so the original function now is just 3 minus 4 x to the power of negative 2. Constant term, so it becomes 0. So calculus step, you'll just get negative 2 times negative 4 is positive 8. X, negative 2 minus 1 is to the power of negative 3. Let's keep going. 4 over square root of x, again you won't really get these in a studies exam, but just be aware that that means x to the power of a half. Square root means x to the power of a half. So you can flatten it by bringing it up and making it 4x to the power of negative a half. Now it's flattened. Let's do the calculus step. Negative a half times 4 is negative 2. X, negative a half minus 1, if you pop it into a calculator, you get negative 3 over 2. You could have also had negative 2x to the power of negative 1.5. That's the same thing. This one just needs to be flattened first. So first two terms already flattened. You can flatten this one by bringing the x squared up here and making it x to the negative 2. So minus 2x to the negative 2. This is still just the original function. So now let's do the calculus step to find the gradient function. 3 times 3 is 9, x squared. That's just an x term, so it just becomes a coefficient, minus 2. Negative 2 times negative 2 is positive 4, x, subtract 1, negative 3. Here we need to flatten the function. There we go, 3 minus x. That's the same as x to the power of a half. Bring it up and make it x to the power of negative a half, and you've still got that 2 there. Now let's do the calculus step. Constant term disappears. That's a negative 1 here. And then we've got negative a half times negative 2 is positive 1. X, subtract 1 from here, you get negative 1.5, or negative 3 over 2. Here we've got to expand first, so write out the double brackets. You might want to write x brackets, x plus 1, close brackets, open brackets, x plus 1. So if you FOIL this part, you'll probably end up getting x squared plus 2x plus 1, but then you've got to multiply all of those by x. So now that times that becomes x cubed, that times that becomes 2x squared, that times that becomes x. That's still the original function, it's just been expanded. Now do the calculus step. F dash x equals 3 times 1 is 3, x squared. 2 times 2 is 4, x to the power of 1, plus 1, because that's just an x term, and that's done. Another one, we have to write out the double bracket and expand first, so write out the double bracket. When you do your foiling, you will get 4x squared minus 2x plus 1. And when you combine the 2 minus 2x's, you get minus 4x. So the original function is still just the 4x squared minus 4x plus 1. Now I'll do the calculus step. F dash of x is 2 times 4 is 8. X, subtract 1 from the exponent, you get just x to the 1. That's just an x term, so it's just the coefficient, minus 4. That's a constant term, so the gradient of that is just 0. So 8x minus 4 is your gradient function. Same again, just expand it out, but notice it's cubed, which you probably won't get in studies, to be honest. You could just write it out like this, x plus 2, x plus 2, x plus 2. What I did is I FOILed this first. You get x squared plus 2x minus 2x plus 4. When you combine the 2x's, you get x squared plus 4x plus 4 times this. Then you have to do all that expanding and so on. And it basically expands to give you this, and then you just do the calculus on that. So that's the original function. The gradient function is f dash x. That becomes 3x squared plus 12x to the 1 plus 12. And then that's a constant term, so it's gone. Here we go. Now we're on to optimization, which is pretty popular kind of thing on a math studies exam, particularly in paper 2. Could be in paper 1, but I've seen it more so in paper 2, but you never know. Optimization, it's basically like real life applications of calculus. And quite often it's joined up with geometry. So you might need to come up with a formula for the volume of a container, like a cylinder or a box. And you might then need to do the calculus on that and then use it to calculate rates of change. So it's very common to see optimization questions on past exams. They tend not to call it optimization in the exam question, but you'll see it's kind of like a real life problem. They usually, and it deals with calculus, they usually require you to work out a formula based on a real life situation, like come up with a formula for the volume of this box, and then differentiate that formula, like find the gradient function, do the calculus, to find the value at which the maximum or the minimum occurs. So maximum volume or minimum volume. You need to remember that the gradient at a maximum or minimum is always equal to 0. That's something you might want to note when we're doing optimization. The gradient at a turning point, at a maximum, like say in a quadratic for example, the maximum point, the gradient at the turning point is 0. Minimum, the gradient at this little turning point is equal to 0. That's really important to remember. Steps involved in optimization. Draw a large clear diagram of the situation if it hasn't already been done for you. Sometimes it has in the questions. Now, step 2 would probably be you'd be asked to construct a formula for the variable to be optimized, like volume, for example, or area or something like that. It should be written in terms of one variable, for example, x. Then you're asked to, quite often, differentiate that formula, find the gradient function for that formula, set it equal to 0, because to find a maximum value or a minimum value, and then solve for x. Step 4, the minimum or maximum may occur at the value of x. So note you can always use your GDC to graph the formulas and find the maximum and minimum points, which is what I'll probably be doing a lot today. Here's a little example where you're using area. So as I said, a real life kind of problem is what optimization's about. And you can use calculus to work out what would be the maximum area of this little enclosure, or the minimum area, for example. So a farmer who has 120 meters of fencing, so like you can make a fence with 120 meters of wire fence, with which to enclose animals, intends to make a rectangular enclosure using an existing wall on one side. So that's why the fence is only this part, and this part. This part's just already a wall. So he only needs to use his fencing for this length, and this length. Find the maximum area which can be enclosed. Normally, to be honest, in exams, I would break this up into part A, part B, part C for you. But I'll just do some examples where maybe it's not always broken up for you. So you can think of it. We want to know, find the maximum area. So we need to find, okay, for example, let's set the width equal to x. So width, we know that in total the fence, he's got 120 meters. And we want to know what width is going to make the maximum area. So, because for example, you could have a tiny width like this, or you can have a long width, in which case it'll be kind of shorter like this. So we want to work out which one gives you the biggest possible area so he can get the most animals into his little pen using 120 meters of fencing. Should he make it long and skinny, or should he make it kind of like square more so, or should he make it kind of like that? Rightio. So again, like the width, we call it x. So draw your little diagram, label the width x. So the reason why I'm calling the length 120 minus 2x is because, remember, this whole length here has to be equal to 120. And if that's x and that's x, the remaining part must be 120, the whole thing, minus these two x's. So that's why I've labeled the length 120 minus 2x. This is quite often something you're expected to do, or just explain. Maybe they'll tell you that in the question and you just have to explain it. Okay, so there's our little fence. So we've labeled length is 120 minus 2x and the width is x. Remembering area, they're asking for maximum area, not perimeter. So area equals the length multiplied by the width. So here, notice the length, basically the width times the length. So I'd write it like x brackets 120 minus 2x, length times width, or I did width times length, which just because it looks better. So this, by the way, I'm calling it the area with respect to x. A of x, see it's looking like something like f of x, isn't it? A of x equals the length, the width times the length. What I'd strongly suggest you do now is expand that out, because you can't do the calculus on it until you've expanded it. So expand it, that times that makes 120x, that times that makes minus 2x squared. This is still just a function that represents the area. So to find the maximum area, what you want to do is you want to find the calculus, do the calculus a dash of x. So remember, normally the original was f of x and the gradient function was f dash of x. Now we're just using a of x and a dash x. So what's the gradient form of this one? If you differentiate this, remember it's an x term, so it just becomes 120. 2 times negative 2 makes negative 4. X, subtract 1 from the exponent to the power of 1. So the gradient function is 120 minus 4x. And remember, at a maximum area or a minimum area, you set this calculus function, the gradient function, equal to 0, because at a maximum or a minimum, the gradient's always equal to 0, and this is a function that represents the gradient. So we know what the gradient is at 0. So you would write, you probably can't see what I've written here, 120 minus 4x. I by accident wrote the original function. Write the gradient function, 120 minus 4x equals 0. See what I've done is you find the gradient function, set it equal to 0, and solve for x. So we're going to solve for x. 120 minus 4x equals 0. That's pretty easy to solve, because you could, I didn't show the step, I kind of crossed it out here. I could write it out here if you want. So we could say 120, if 120 minus 4x equals 0, 120 must equal 4x. You start to rearrange and solve. If 120 equals 4x, then it's pretty obvious that x has got to be 30, because 4 times 30 is 120. So x equals 120 divided by 4, which equals 30. So we found out that to get the maximum area, we need this length, the width, to be 30. That's what we've just found out. And the length should be 120 minus 2 times 30. So 2 times 30 is 60, 120 minus 60 is 60. So to get a maximum area, we need a width of 30 and a length of 60. Amazing stuff. So we just, therefore, to find the area that needs to be enclosed, you would just therefore take 30 times 60, because area is length times width. You could also do this. What I did was I just found out what x is 30, then I just substituted it back into the original area formula, not the gradient formula, but the original one. So if you sub it back into 120 times 30 minus 2 times 30 squared, you get the same thing, 30 by 60, which is what I said, 1800 meters squared. So that's the maximum area you can make with 120 meters of fencing in this situation. And you want the maximum area, of course, because then you can fit the most little animals in there. So you can kind of see how it's kind of useful to some extent to this farmer to do calculus. Let's do some more ones. See, it's very geometry based, a lot of these questions. A square sheet of metal, here's a big square sheet of metal, 12 centimeters by 12 centimeters, has smaller squares cut out from its corner. Little squares cut out from its corner. And because when you do this, you can fold it up and make a little box or a tray. What size square should be cut out so that the sheet will bend into a box like this, and it will hold the maximum amount of liquid? So maximum amount of liquid requires maximum volume. So what we want is max, you might want to write it down, we want to know max volume. And they said what size square, so they just basically want to know what length and width do the square have to be. So what I did, the little squares, I labelled their length and width x, because squares have the same length and width, so call that x, this length here is x, that length here is x, x by x, x by x, x by x. Nice. And remember to find volume. Volume equals, good geometry practice this, length by width by height. Length times width times height to get the volume. If you folded this up into a little box, you know its height would be x, because these little flaps would make the height. So the height would be x. So I've put that first, just because it's easy to put the x first. Its bottom length would be 12 minus 2x. Why did I say that? It's because all of this is 12, but this little length here would be the 12 minus x minus x. So that's why I called this little width here 12 minus 2x. And this length here, similarly, will be the same thing. That length there, the length and width will be same thing, 12 minus x minus x. So that's why the other length is also 12 minus 2x. So if you folded it up, it would be 12 minus 2x by 12 minus 2x by x. Written like this. Now you have to get good at your expanding and foiling here. So what I did is I left the x out the front, and I foiled and expanded all of the double brackets first. So 12 by 12 is 144, 12 by minus 2x is minus 24x, that times that is minus 24x, that times that makes a plus 4x squared, and minus 24x makes negative 48x. So I just got lazy and didn't show that middle step. So all of this expands and combines to be this, and then you now have to do this. You have to expand all of that. So x times 144, 144x, x times that, negative 48x squared, x times that, plus 4x cubed. This is still your original function, it's the volume function. Remember now, next step, do the calculus step. V dash of x, like finding f dash of x. That's an x term, so it just becomes a coefficient, 144. 2 times negative 48, negative 96, x. Subtract 1 from the exponent, you get x to the 1. 3 times 4 plus 12, x. Subtract 1 from the exponent, 2. And remember, at a maximum volume, the gradient function, not the original, but the gradient function is set equal to 0. Set it equal to 0 and solve. So what I did, I just rewrote it out as 12x squared minus 96x plus 144 equals 0. You could totally factorize this if you wanted to, or you could solve it on polysmalt. So let's make a little note. Say, or solve using Polysmalt app. So solve using Polysmalt app. Let's practice doing that again. And then you'll see why I kind of put it into that order. So remember to use Polysmalt. This is a quadratic, that's why we can solve it in Polysmalt. So remember, you go apps, select Polysmalt wherever it is for you. Not Simi equation solver, press enter. We want poly root finder, that's how you solve a quadratic. We want that to be 2, that's all good. Next. So you've got to put the coefficient of the x squared term in first. So that's 12x squared. So let's put 12. The coefficient of the x term is negative 96, so negative 96. The constant term is positive 144, so just 144. Then click solve. Got two answers, x equals 6, x equals 2. So you didn't have to do the factorizing and everything if you didn't want to. You can just solve on Polysmalt. Two answers, x equals 6, x equals 2. Pretty interesting. Let's check these out what they wanted. What size square should be cut open? So is it a 2 by 2 square or a 6 by 6 square? Let's see. So we've got two answers. So that little square that got cut out from the corners could be a 6 by 6 square, or it could be a 2 by 2 square, because according to our diagram, the square is x by x, x by x. It's always good to check, does one of them not make sense? Sometimes you need to reject an answer because it doesn't make sense in terms of the real problem. And the one that doesn't make sense is this one. So this one should be rejected because, for example, if that length here is 6 and this whole length here is 12, then 12 minus 6 would just make this 0, which doesn't make sense at all. You wouldn't even have a box anymore, would you? So 12 minus 6 is wrong. We need to reject x equals 6 as the answer. But if you did 12 minus 2 just means this length here is 8. That's perfectly okay. So we reject this answer and we accept that answer. So that was just pointing out that you can't have 0 as a box length. So the answer is a 2 by 2 sheet. They said what shape square? It would be this one here. So let's put maybe a little arrow to point that out. It would be this little one here, a 2 by 2 sheet. I'll just save what I've done so far. As I said, mostly these questions get broken up into part A, B, and C first. And maybe, maybe quite often they'll not expect you to totally do this kind of thing from scratch, but maybe they'll tell you that's the answer, and part A would be just show that this is the answer. And then because they gave you that in question A, you can then follow through and do question B and C anyway. It's quite often what they do. Let's do some more ones. We've got a rectangular sheet of metal, measures 8 by 3 centimeters. Same thing again, you can see it's the same thing. Feel free to draw it all again. But instead of being 12 by 12, this whole length here is 8. And the other whole length is 3. No, what was it? Yeah, 3. So this whole length here is 3. It's not 12 by 12 this time. So that's why you've got two different kind of equations. So a little corners have been cut out, x by x, x by x, x by x, x by x. But this time, this little length here will be 8 minus 2x, not 12 minus 2x, because 8 minus x, x. And then this little length here will be 3 minus 2x, because it'll be 3 minus x minus x. That's that little length here. Same thing, find the maximum volume. So we need to solve for x eventually, and then once we've got x, we'll sub it into the volume formula, or work out the length, width, and height, and then calculate the volume. So here's our formula. We've got x 1